Hello and welcome to this video about matrix proofs. In this video we'll prove something about augmented matrices. That if two augmented matrices are row equivalent to the same matrix in reduced row echelon form, then they have the same solution sets. So let's start the proof. We'll let these two matrices AG and BG be these two augmented matrices that are row equivalent to the same matrix in reduced row echelon form. We'll just write this down mathematically. This function gets the reduced row echelon form of a matrix and produces the same value for both of these matrices. And for convenience, we'll set this matrix RG to be the reduced row echelon form of both of these matrices. So I guess that you're extremely familiar with augmented matrices. They have an extra column called the solution column. That's the last column, and that contains a solution vector to the equation, and a main body that contains all of the equations in the form of numbers or coefficients. The body is usually a square matrix, but can be longer and is usually never shorter. And these are the other two matrices BG and RG that can be divided up the same way. So I'll just scroll the screen up to make more room. With matrices, there is usually a list of row operation matrices that when multiplied on the left of a matrix, converted into reduced row echelon form like this. We can define a new function called the Gaussian elimination function, which is the product of all of these matrices. I didn't like the proof that was given in the textbook, which described the augmented matrix in terms of equations with single variables, because I felt it wasn't clear enough. So I decided to try to prove it using this function. And it's worth noting that if the reduced row echelon form of a matrix is the identity matrix, then the Gaussian function of a matrix is its inverse. So the Gaussian function is a sort of generalized inverse of a matrix that's usually used for matrices that might be non-invertible. We can then write out this equation, which is how to get the reduced row echelon form of a matrix by multiplying it on the left by its Gaussian or generalized inverse matrix. And this matrix is equal to R because we defined R to be equal to this value. We can also use this Gaussian matrix to get the reduced row echelon form of the body of the first augmented matrix AG, because it's only not including the last column of the corresponding augmented matrix. And so multiplying A by this matrix will give us the reduced row echelon form of A. And so it will give us R as we defined it earlier, because it refers to the main body of the augmented matrix. And applying this matrix to the last column of A will give us the last column of R, because all of the columns of any matrix can be independently multiplied by the Gaussian matrix to give the same result. We can similarly multiply B on the left by its Gaussian matrix to give us the reduced row echelon form of B, which will give us R, because that's what we've set R to be equal to. And multiplying the last column of B on the left by this Gaussian matrix will give us the last column of R, called little r. So now to look at the solution sets of these matrices. The augmented matrix A is really this equation, packed up into one matrix, where the variables to be solved are written down somewhere else and remembered, but not stored in the augmented matrix. We'll multiply this equation on the left by the Gaussian matrix of A. This will give us the reduced row echelon form of A as defined, and also the last column of R. And we can substitute R in here, so this represents a solution set. We don't have to calculate it further. Then we can get the equation that the augmented matrix BG represents. We can then multiply this equation on both sides by the Gaussian matrix, which represents all of the row operations. This will give us this equation. We already have the last column of R on the right-hand side. And so this will be the solution set for the second augmented matrix, which is the same as for the first, since we have to solve exactly the same matrix vector equation. So that's it, we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write any helpful thoughts and ideas in the comments, and to share this video. And thanks a lot for watching.